Welcome back to ECE 320A. We're in Unit 12, which is our two-port network or two-port circuit unit. That's going to have homework number 12 due at the end of this unit, and this material is coming to us from Chapter 18. In this video, what we want to look at is actually finding from a circuit these two-port parameters. And here is the circuit that we want to investigate. It's a T network. You can sort of imagine the T that is illustrated by this network. And that's now what we want to try to find. We want to try to find the Z parameters, which are the Z11, the Z12, the Z21, and the Z22. We have three different parameters in this circuit. Now we want to actually find four parameters that are consistent with this set of equations, these two equations where I1 and I2 are independent variables and V1 and V2 are dependent variables. So we're trying to now identify Z11, Z12, Z21 and Z22 from that T network. And the way that we will do it is, in fact, we are going to go ahead and simply apply. You could do this many different ways, but let's just now say that we apply a voltage source. You could apply a current source. You just need to decide how you want to energize this circuit or analyze this circuit to try to find the Z11, the Z12, etc. And here I'm now saying, oh, let's just go ahead and assume that, well, maybe it really doesn't matter. So let's just go ahead and say that let's apply current sources, independent current sources. So this current source then must be supplying I1, and this must be supplying I2 in that direction in order to be consistent with the way the two ports are defined. If that's the case, then we have I1 coming here and I2 going counter to that, so it's not the classical mesh analysis that we will be performing in finding these particular variables. But we now want to interrelate the V's and the I's with these three different resistors in this T network. So let's do that by simply writing KVL around the left mesh. And this is now after we've applied these two different current sources, and because this is a linear system, we can actually look at using superposition when it's helpful to us, meaning we can set I sub 2 to 0 and analyze the circuit. We can set I sub 1 to 0 and analyze the circuit. Let's go ahead and assume right now that both sources are energized and they're now playing into creating V1 and V sub 2 in this interconnected circuit. If that's the case, then in the left mesh we have minus V1 starting in the lower left-hand corner plus 1, that's the horizontal resistor on the left, times I1 plus 2, the vertical resistor, times the net current going down through that resistor, which in fact is the sum of I1 and I2. So that's what's a little different than the normal mesh equations. These mesh currents, so to speak, or these sources are applied such that they are not flowing in the same clockwise or counterclockwise direction. One's clockwise and one's counterclockwise. But this is now from the left-hand mesh, we obtain this equation, And we can now solve for z sub 1, 1 by simply saying, in fact, if we had I sub 2 equal to 0, and how do we have I sub 2 equal to 0? Well, we open up the output terminals. So we remove that second source, I sub 2. We set I sub 2 to 0. Opening that up now gives us a way to find V1 and V sub 2 with only I sub 1 being present. And that then says that if we're now eliminating I sub 2, we should now be able to find, based on some KVL equations, Z sub 1, 1 and Z sub 2, 1 from this relationship of KVL relating V1, I1, and I sub 2 with I sub 2 set equal to 0. Or, finding Z1, we're going to open up the output ports, or we're going to go ahead and set I sub 2 equal to 0 in this relationship. And now we have minus V1 plus I1 plus 2I1 is equal to 0. Or we now have V1 is equal to 3I1, and that now says actually that Z11, if we look at the definition or the equation, we can find Z11 if we look at V1 over I1 with I sub 2 set equal to 0. V1 is 3I1 over I1, or that's 3, so that Z11 we've now determined, and because we had resistors, this is now just a constant value of 3. We can also now look at finding Z sub 1, 2 from this equation in the left mesh by now setting I1 equal to 0. You could do it in different ways, but let's now look at computing Z12, so that now we're going to set the left current, or the current on the input port, equal to 0. And now we have minus V1 plus, there's I1 equal to 0, plus 2 times 0 plus I sub 2. And we now have then that V1 is equal to 2 I sub 2, or writing it a different way or slightly rearranging this, we can now say that Z12 is equal to V1 over I sub 2 with the input port open, or with I sub 1 equal to 0, and that now gives us a value of 2 for Z sub 1, 2. Those two values for 4 of the Z parameters we've now found by simply writing one KVL equation, and that KVL was on the left mesh. Let's now write a KVL equation for the right mesh, and that's now going to be minus V sub 2 coming up from this lower right-hand corner, minus V sub 2 plus 3I sub 2 plus 2 times I1 plus I sub 2. Then at the right mesh, we have minus V sub 2, just writing down what I just tried to illustrate in the scrolled up version, 3I sub 2 plus the vertical resistor, which had a value of 2, times the sum of I sub 1 and I sub 2. And now we can find the two remaining Z parameters of the 4 total Z parameters. We can solve for Z sub 2, 1, and if we look at this particular definition, if we want Z sub 2, 1, then we need to set I sub 2 equal to 0 in the second equation. So Z sub 2 will be found by setting the right independent source equal to 0. And that now gives us V sub 2 is equal to simply 2I sub 2. Whoops. I sub 2 is 0. It's not going to give us that. It will give us 2 times I sub 1. And now I can see why I was making the mistake, is that should have been I sub 1 plus I sub 2 there. So that now, if we form the ratio to identify Z sub 2, 1, that's the ratio of V sub 2 over I1 with I sub 2 set equal to 0. That's now equal to 2. One more of the Z parameters of the 4. We've already identified 3 of the 4. We now are trying to find Z sub 2, 2, and we can find that based on the definition by finding a relationship that involves V sub 2, I1, and I sub 2, and setting I sub 1 equal to 0, or setting that leftmost source, or the source at the input port, equal to 0. And now we have, if I can remember my subscripts, we now have minus V sub 2 plus 3I sub 2 plus 2I sub 2 is equal to 0. Or Z sub 2, 2, which is now equal to the ratio of V sub 2 to I sub 2 with the input port open, or with I sub 1 equal to 0. That's now going to be 5I sub 2 over I sub 2, or 5, and that's now our Z sub 2, 2. And we could summarize that by saying we've now related this set of voltages V through an impedance matrix and connected it to the independent currents I's, and now Z, our 4 Z parameters are 3, 2, 2, and 5. For that particular T network, we've now extracted 4 variables from the 3 resistor case, but now if somebody needs that particular circuit, we can now model that by these 4 Z parameters anywhere we want if we have started with that T network of resistors.